Okay, this lesson is on the inverse of a function. So the third learning goal here is we're learning to make connections between functions and their inverses given various representations. So different representations like really just a graph and an equation. Table of values would be similar as well. So we'll start off with this situation, Cheap Flicks discount movie rental service. So you got a membership fee of $10 per year plus $2 per movie. So 10 is like your fixed upfront cost, and you get your $2 slope. So a customer's total movie cost for the year is a function of the total movies he's rented. If X is the movies he's rented, f of X is the total charge, then f of X is 2X plus 10. If you want to instead like figure out how many movies you can rent based on how much money you have, you can actually rearrange the equation. And if you rearrange it once and for all, you can sub different numbers in. So that's what the inverse of a function is going to actually be. So instead of x being the number of movies, where x is going to be the total budget. So it's the input. And then we're going to call g of x the number of movies rented. And so you can kind of figure out what would that equation be so that it rearranges and solves every time. When you think about it, if you put the 10 on the other side and divide by 2, you can say g of x is x minus 10 divided by 2. And this is what we're going to call an inverse function. So it does the opposite. So it switches up the role of what's the input and what's the output. In learning goal 3, we're learning to make connections between functions and their inverses. They're given representations to solve problems related to inverses. First success criteria is finding the inverse given a graph. So could use linear quadratic graph or also just points on a graph and connect the graph to the inverse. And then success criteria 2 is if you're given the equation, you find the inverse. And there'll be 2 methods that we're going to talk about for that. And success criteria 3 is relationship between domain range and the domain range of the inverse. So first off, the inverse of a function is really the opposite or reverse of the original function. So where x was the input, now we're going to switch that up. And so x will always be the input, but if we want the independent variable to be, say, cost, and then dependent variable being the number of movies, we switch what x and y is. And instead of writing f of x, we write f inverse x just to denote that the inverse is a function and it's related to f. So start off with inverse operations. So if you notice that like what we're doing is we're taking the inputs and multiplying them by 2 and adding 10, what we can do for the inverse is subtract 10 and then divide by 2. So the inverse operations in the reverse order. So the inverse, f inverse of x is x minus 10 over 2. Finding the inverse on a graph. So if we're switching x and y, if you have the points on the graph, how do you find the inverse points? And so just going one at a time, if the input's -3 and the output's -1, we'd switch this up so the input's -1 and the output's -3. And so graphing them on the same grid, -3, -1 becomes -1, -3. -2, 2 becomes 2, -2. -1, -4 becomes -4, -1. 0, 3 becomes 3, 0. 1, 1 becomes 1, 1. It doesn't change. 3, 4 becomes 4, 3. I missed one there. 2, -1 becomes -1, 2. And 3, 4 becomes 4, 3. So you notice you actually have this like point, this line y equals x. So what all these points are reflections of the red ones are the reflections of the black ones. So like this point actually corresponds to this point here. So they're reflections. These guys are reflections. It's not the easiest to see right now, but we'll come back to that. So what happens is just the x and y switch. Are the original points a function? So do the original points pass the vertical line test? Are the inverse points a function? So do the inverse points pass the vertical line test? And you're going to find out that they don't. And so the red ones actually fail the vertical line test. And so You'll have to answer those questions like, is the inverse a function? That's going to come up in the quadratic. What do you notice about the domain range of the original versus the inverse? We're going to get to that as well in this lesson. Coming up with an equation, so using inverse operations, you can try this yourself. So multiply by 2, add 5, becomes subtract 5 and divide by 2. And so the input actually gets subtracted 5 and divided by 2. By switching the variables, we put y back in just because we can switch it nicer. We switch x and y, and then solve for y. Subtract 5, then divide by 2. And we get y equals x minus 5 over 2. And we can write it f inverse of x equals x minus 5 over 2. Looking at a quadratic, quadratic, by the way, it has to be in a vertex form to do this. Otherwise, you can't actually solve for x. And so the inverse has to be in in the base transformed form of the quadratic. And if it's not, you'll have to complete the square to actually put it in that form, which we haven't done yet. So we won't be completing the square until the third unit, but you need this vertex form to do it. So the original function, actually, what you do to the inputs, you subtract 1 and then you square. The order really matters here. You multiply by 2 and then you add 3. And if you're having trouble figuring out that order, just actually sub something in and see what you do to it. What are the order of the operations that you would do? Brackets, exponent, multiplication, addition. The inverse function, we actually go in the opposite order, and then we do the inverse operation. So instead of adding 3, we subtract 3. Instead of multiplying by 2, we divide by 2 or multiply by half. Instead of squaring, we square root, and we include the plus or minus. And instead of subtracting 1, we add 1. And so just one at a time, we start by subtracting 3, dividing by 2, square rooting, and then adding 1. By switching the variables, notice that we didn't write f inverse of x, and or g inverse of x, and there's a reason why we didn't do that. And so you can think about why for a bit, and we'll come back to it. By switching the variables, so again, we put y in again, and then we switch x and y, and then we solve for y by subtracting 3, then dividing it by 2, then take the square root, plus or minus, and then add 1. And so that's our inverse function. Exploring the graphs, so if you just graph those guys in a graphing calculator, we actually want to come back to this idea of the line of y equals x, and this is a more symmetric graph, so you'll be able to see it a little bit better. If you graph the line y equals 2x plus 5, so f of x equals 2x plus 5, if you switch the x and y coordinates of every one of the points, and so 0, 5 becomes 5, 0, -5 stays the same, then what you can do is you can actually find the inverse line, which is like the y-intercept of -2.5 and a slope of 1/2. That's x minus 5 over 2. But you can actually find the inverse by doing that, and so just switching x and y coordinates will give you the inverse. On a quadratic, if you had the quadratic in vertex form, it is shifted to the right 1 and up 3, and it's vertically stretched by 2. Switching the x and y points, so there is a 0, 5 here. You can see if you plug in 0, you get 5. So that point 5, 0 and 5, 2 and 2, 5, you can see that those points are switching as well. Maybe you turn your head sideways, you almost see that reflection over that line y equals x. And you can also notice that the inverse function that we calculated in the last slide is actually 2 square root functions. One's positive, one's negative. So one will actually be vertically reflected. To see that a little bit better, to connect it with the transformations we've seen in the past, you can write it like this. And so instead of writing divide by 2, you write multiply by 0.5. You can see that vertical stretch by 2, the horizontal shift right 3, and up 1. I really love looking at the transformations because you can see like this is a vertical stretch by 2. So vertical, so because x and y change, then you want a horizontal stretch by 2. So it also backs up the fact that 0.5 is a stretch, not a compression. And up 3, if you think about that horizontally, that's right 3, and so that's why you got a minus 3 here. A right 1, thinking about vertically, is an up 1. And so it really backs up this idea of transformations when you look at it like that. If you state the domain range of the function and the domain range of its inverse, you'll notice a pattern here. The original function has domain of all real numbers. The range is greater than or equal to 3. If you look at the inverse, domain is all real numbers greater than or equal to 3, and the range is all real numbers. So you can see this really just switching up the x and y's. Is the graph the inverse of function? You can see the red graph here. The original is a function. We knew it's quadratic, but like the double root graph here is actually failing the vertical line test. And this is the reason why we wrote it as y equals and not g inverse equals. If you want to write it, so to write it with like inverse function notation, you can break it up. So the equation of the inverse would actually be g inverse of the positive 1 plus 1 when y is greater than or equal to 1. So when y is greater than or equal to 1, then this will actually work. When y is less than 1 or equal to, it doesn't really matter. The g inverse is the negative, and so it's the same thing. But that's when y is below 1. You could say equal to 1. It's really the y. It doesn't really matter, but that's just kind of breaking it up. That's the reason why we couldn't use the inverse notation before, because it wasn't a function. But if you now make it a function, so this part here now is a function, and so is this, and together they make the inverse, you can write it like this now.